As I mentioned, we're most fortunate that Professor Julian Savulescu has agreed to speak for us today for a short time in Dr. McNab's absence. If you're fortunate enough to be with us for the La Trobe Centre for Dialogue annual lecture here at St Michael's just a week or so ago, you will have heard some of what Professor Savulescu had to say about ethics and medicine in this astonishing age. And we're very grateful that you're going to give us a little bit more to think about today. Please welcome him again, Professor Savulescu.
Well, thank you very much, Dr. Campbell. So I'm a fill-in, and this is not a sermon, it's just a talk. And I've given 2 public talks, so I've had to try to find some new material, so hopefully this won't be too boring for those of you who've heard me talk before. So I was asked to talk on the future of science, and this has been one of my fascinations because I originally did medicine and actually a degree in neuroscience. I had 2 monkeys and worked with Mal Horn, who's now the Deputy Director at the Florey Neurosciences Institute. And when I decided to go into philosophy, I was always very interested in the cutting edge of science and what was happening and the issues it threw up. And so I haven't produced a bionic ear or a bionic eye, and in that sense haven't done any of the extraordinary good that Dr. Allen's done. But I tried to think about the trajectory of science and some of the issues that it's raised. And the first thing to notice about science is that it's exponential. Some of you may have heard about Moore's law. This is the theory that Moore proposed many years ago, that the power of transistors doubles every 2 years. And that law has been obeyed for decades now. And computing power continues to double roughly every 2 years. But the same applies essentially to all science, to all knowledge, so the biological sciences, neuroscience, and so on. So science today is extraordinarily powerful, but it's getting more and more powerful at an ever-increasing rate. So it was 50 or 60 years ago that Watson and Crick discovered the structure of DNA, the molecule of life, that it was a double helix. And it was roughly 40 or 50 years after that the whole human genome was mapped around the year 2000. So all function of those instructions are now understood. So all the major single gene diseases have now been identified. So people who want to have a child today can have carrier testing for over 200 conditions and identify whether they're both at risk of having a child with that condition and be offered either artificial reproduction, creating a baby outside of the womb, and testing of that embryo for those conditions. This is an extraordinary development, but it's really only the tip of the iceberg of what's been happening. Not only can we test for the genes that people have, but in principle we can modify them. So genetic engineering has been going on for 30 or 40 years, mainly in animals, changing the characteristics of animals to allow us to study diseases, to allow us to identify how the eye develops or the brain develops. But this involves transferring genes across animals, between humans and animals. And this is an extraordinary thing when you think about it, that humans can create life that would never have existed naturally. You're all familiar with the debate on cloning and its relationship to embryonic stem cell research. That's another area where, for the first time, human beings have been able to do something that occurred naturally in nature when identical twins are formed. And we can do that easily today. We can split an embryo. But we can also, in principle, create humans that are genetically identical living at different ages. Even more radical than these sorts of advances is what's called synthetic biology. A few years ago, Craig Venter, who did as much to discover the genes that contributed to the human genome as the rest of the world combined, has set up his own institute looking to create life from the ground up, from the basic building blocks, without moving genes across different animals, but by taking chemicals and constructing DNA from them according to his specific design. Now, he's already done this in a very basic bacterium, and what he did was take an existing bacterium and remove its instructions and insert the ones which he'd or his team had constructed. And he created a different kind of bacterium. Now you might say, well, so what? You know, it's just another bacterium. But it's proof in principle that you can create a new life form by designing it, not by modifying existing genes, but by using the chemicals that are in the ground and around us to create life itself. There was a big debate about whether he had really artificially created life, something that in the past we thought only God could do. Some people said no, because he used the apparatus of the cell, of an existing cell, which he didn't construct, and he only constructed the instructions to drive that apparatus. Now, I think this is an interesting question. I don't think he's entirely created artificial life, but I don't think it really matters. Because what matters is that this opens the door to creating life forms that are completely different to anything that existed in the world until this time. We've been able to do that with genetic engineering, it's true, but this opens the door to creating new sequences of new proteins that have never been produced by an animal. So it's a very, very incredible time to be able to populate the world with organisms that have never existed. And indeed, science is also trying to repopulate the world with organisms that are now extinct. There's a project, I think, in Australia on the Tasmanian tiger to try to bring this back through using cloning to create a live-born tiger. And the same with the mammoth. That's another project. These are all testimony to the incredible biological revolution that is occurring all around you, but you don't see it because you're not a scientist working in a laboratory and you don't read advanced scientific publications. But this is an incredible time which humans have never experienced, the ability to create and change life itself. This is being used to treat diseases, but it's also being proposed as a way of removing pollution, of generating new energy, or indeed of generating new ways of approaching computing problems. There are also advances in the neurosciences of understanding the brain. We've heard about epilepsy today, and this morning Professor Cook described technologies that can look into people's brains, not just looking at the structure, but looking at the way they're functioning, the way the blood is moving in the brain, the way the neurons are being activated. And indeed in Europe there's a project that is parallel to the genome mapping project of a decade or so ago, where they're trying to map the connections of all 100 billion neurons. I can't remember how many there are now. It's an extraordinary, it's one-fifth the size of the Milky Way in terms of numbers, the neurons in the brain. So this is an extraordinary time. This is being used to look at whether people are lying in court cases, and ultimately will enable us to change the sorts of problems or the sorts of dispositions that Professor Cook is now looking at through the use of drugs and other technologies. On Friday, the IPCC's latest report on climate change was released, and again there are predictions that the Earth will heat by 2 to 4 degrees over the next 90 or so years, and there's no evidence that we're adequately addressing this by stopping consumption or reducing carbon emissions. But science affords us today with many alternatives. It affords us with nuclear energy, and the third generation pebble bed reactors would be a way in which China could reduce its emissions without having to burn brown coal. But it also is offering the possibility of changing the climate intentionally. So far, for hundreds of years, we've been changing it unintentionally through industrialisation. But today, knowledge that science has afforded us opens up the possibility that you could correct climate change by altering the climate. How could you do this? The first way is by solar radiation management. This involves putting sulphur particles in the outer atmosphere that reflect sunlight. How do we know this works? Well, this is what happens when volcanoes erupt, such as Mount Pinatubo a number of years ago, and the Earth's temperature drops. There's been attempted experiments to look at putting sulphur particles in the upper atmosphere as a cheap, easily deployable method of reducing the Earth's temperature. It has risks. If suddenly you stop putting the sulphur up there, the Earth will rapidly heat up because you've been producing a lot of carbon dioxide in the meantime. So a more attractive alternative is so-called carbon dioxide removal strategies, where you suck carbon dioxide out of the atmosphere. There are a number of ways you can do this. One is by using chemical reactions in the sea to suck the carbon dioxide out. And this is a very active line of research. In fact, I think the IPCC recommends that research into these geoengineering strategies be undertaken as an exit strategy if reduction in carbon emissions doesn't take place. Now, there are still great challenges that we face as a species in terms of disease and in terms of the factors that affect our lives. And science hasn't provided solutions to everything. Malaria is still a great challenge, and many of the most common diseases have been given little research attention. Given the extraordinary power of science to correct these sorts of problems, one basic principle is that we are responsible for not just what we do, but also what we fail to do. So if we fail to undertake research into common diseases or common conditions or grave threats, okay, we're responsible for the outcomes of that. So if you obstruct a line of effective medical research that would cure 100,000 people per year, you're responsible for the deaths of 100,000 people per year. So this idea that we're responsible for not just what we do, but for what we fail to do is a very important one today, because our powers to change the world are extraordinary, not just through our actions, but also through our omissions. Now, many people deny that sins of omission are as bad as sins of commission. But here's a famous philosopher's parable, if you like, that James Rachels, an American philosopher, gave in 1975 in an article in the New England Journal of Medicine, where he was defending active euthanasia as a way of relieving suffering. And he said, imagine two men, Smith and Jones, and each of them have a 2-year-old cousin. And if their 2-year-old cousin dies, they'll inherit $1 million. So Smith decides he wants the money and decides to kill his nephew. So one night the child's in the bath, he goes into the bath and he drowns the child. And he pretends it was an epileptic fit and the child hit his head on the tap and died as a result. This is murder. It's clearly wrong. It's an act that kills the child. Jones also decides he wants the $1 million, walks up to when his nephew is having a bath, walks in, and the child, just as he walks in the door, slips and hits head on the tap and falls unconscious face down in the water, not dead, but unconscious. And Jones stands ready to push the child's head under, but as luck would have it, the child dies all by itself. He didn't kill the child, he only allowed the child to die. Rachels persuasively argues that both Smith and Jones are equally bad people. That although Jones only allowed the child to die, what he did was equally blameworthy. Indeed, the concept of moral responsibility, the concept of whether you're responsible for some outcome, is a function of two factors. One is not intentionality, not whether you intend something to happen, but foreseeability, whether you could foresee that a result of what you did or failed to do will result in some bad consequence. And the second factor is avoidability, whether it was in your power to change that outcome. But this account of moral responsibility doesn't appeal to whether we acted or omitted. It's simply a fact of whether we can foresee the consequences of what we do. So one of the important lessons of a moral analysis of the advance of science is, given its extraordinary potential, we need to have very good reasons to obstruct it if it's aiming at some worthwhile end, like the curing of a disease. And this is precisely why the Lockhart Committee in Australia recommended research into embryonic stem cells and cloning. Okay, so that's the good side, the bright side. The dark side of science is that with any great advance in power comes an enormous potential for abuse. Okay, so penicillin saved millions of lives, extraordinary advance. Yet the advances in the biological sciences that I described, which are going to continue to increase in power, will mean that within a decade, people can do what Craig Venter is trying to do at a more basic level, using subunits purchased on the internet to create viruses of their design. So smallpox was eradicated in the 70s through an amazing program. It's now gone from the world. It killed more people than any other virus. It kills 1/3 of people who contract it, 1/3 of people who come within 3 feet get it, and it takes 2 weeks to manifest itself. Within a decade, it will be within the power of hundreds of thousands of people to make smallpox in a relatively simple laboratory. That's something, again, that humans have never faced. So not only have they never faced the possibility of creating bionic eyes or bionic ears, but they've never faced the prospect that large numbers of people could kill millions of other people. So knowledge begets knowledge, and science is ever increasing in our power. So more than at any other time, we need to recognise that science can't provide answers to how science is used or regulated or deployed. So how we decide to publish the knowledge, for example, of research that can give people the instructions, the plan for killing millions of people is a choice that we have. It's not inevitable that we publish every finding. Recently, scientists published the changes that enabled them to cause bird flu to cross over into humans. And there was a great discussion about whether all of these findings should be published or not. We will face more and more challenges that are not scientific challenges, but that are ethical challenges about how we regulate science and how we use science. Now, I talked about the extraordinary power of science and the importance of ethics. As I said, science is about the way the world is, will be, could be, but it doesn't tell you how the world should be. It can't tell you alone whether you should employ geoengineering or not employ geoengineering. It can't tell you whether you should conduct research into genetic modifications that make viruses more lethal or not. Those are human choices. And around the middle of last century, we had already achieved a power that humans had never had before in virtue of science, and that was through the extraordinary advances in physics in the early part of the 1900s and the development of nuclear weapons. So around the middle of last century, for the first time, humans acquired the capacity to destroy the planet. And thankfully, that's not so far happened. But not only is this the day to celebrate Florey and the discovery of penicillin, it's the day to celebrate another event that occurred 30 years ago on the 26th of September, 1983. So in the early hours of the morning on that day, the Soviet Union's early warning systems detected an incoming missile strike from the United States. Computer readouts suggested several missiles, I think 5 missiles, had been launched by the US. And the protocol for the Soviet military was to retaliate immediately with a nuclear attack of their own. Maybe some of you have read this story recently in the press, but on that day, a duty officer, Stanislav Petrov, had the job of registering apparent enemy missile launches. He said, I had all the data to suggest there was an ongoing missile attack. 29 out of 30 warning systems had operated. And he said, if I'd sent my report up the chain of command, nobody would have said a word against it. But he decided not to register. He decided not to act. He decided not to tell his superiors and decided that this was a false alarm. He said that he didn't know whether he was making the right decision, but he knew within several minutes it wouldn't make a difference. And after 30 minutes, he realised that it had been a false alarm. What had happened was that the Soviet Union had introduced a state-of-the-art computer system that monitored data from a new satellite. And the satellite, this wasn't known at the time, the satellite picked up reflection from a number of clouds that it registered as being missiles launched by the US. Now, you might say that, well, they wouldn't have retaliated. In fact, there's good evidence to suggest that they would have retaliated. A senior KGB colonel said the spirit at that time was a kind of paranoia that the Americans were about to initiate a first strike. I don't know, this must have been about the time of Ronald Reagan. And just a few weeks before, on September the 1st, the Soviets had mistakenly shot down a Korean aircraft that they had believed was a military plane, killing 269 civilians, including a US congressman. So there's good reasons to believe that Petrov was right, that if he'd passed this information up the chain of command, this would have resulted in a nuclear holocaust. Now, he also made the point that he was the only civilian-educated person. Everyone else who could have been in that job at that time was a military-trained individual who'd gone, a career soldier, who were used to obeying commands. And the protocol was absolutely strict. If you got this information, you had to pass it on. And he said, we're probably lucky that it was him on duty rather than somebody else. Now, this is a great example where, arguably, Petrov saved more people than Florey through his decision to omit to act. And it was based, he said, on his gut. But in fact, it was probably based on his humanity and his own ethics about what he should do. And I think this is a great example where a single individual can change the fate of the whole world. But it's a decision based on their own ethics and values. And for that reason, what's going on at St Michael's is so important, not just for the community here, but for the whole world. So it's a great privilege to be able to reflect on the future of science, and I hope that the work that is going on here will have an even greater penetration in the future. Thank you.